let's say a car bumped against it, open cavity, like the pictures that I showed you before. So, as I said, when water is in the cells, in the lumen of the cells, most of the hyphae cannot penetrate. When we do that, we reduce the crown, the spread of the decay accelerated dramatically. And later on we found out, oh yeah, well, Lynn Body explained that already when he used it before, because when you take down 1/3 of the crown, approximately 1/3 of the cross-sectional area falls dry, so there is no water anymore sucked through these cells, and then the hyphae of the fungi can enter these cells. When there is a defect at the stem base, typically trees react by building more wood. Yeah, you know that. They are getting bigger. These are trees on the screen now. The one left is, I think, from San Francisco. There's one from Perth, Australia, one from Seattle, one from Madrid, one from Moscow probably, and the one in the middle is from Heidelberg. This is the kind of the principle behind, because why we call it self-referencing. That means we take this cross-section here, where this is the defect, and we try to evaluate the safety of this cross-section by comparing it with the intact cross-section of the same tree. Because the intact cross-section of the same tree is the response of the tree to the wind load. The material properties are homogeneous. That means basically it depends on the size and the shape of it. Yeah, by just seeing the size and the shape, you can easily predict where it will break. And that's the case as soon as the material property is homogeneous. The banana is obvious. It's very strong under tension, can pull, and it's very strong, but it's weaker under compression. What do you think? In which direction is it weaker? In this direction or in this direction? What do you think? This one is weaker?
I think the other way will snap, that will compress together.
Advanced tree decay detection with Frank Rinn. It's time to get fruity with the vegetables.
Do you know how monkeys open the banana? 1/10 of the force than by pulling it apart attention. Twisting is the easiest way to crack material that are soft in the center, like decayed wood, and that are having a fibrous, strong outer part that is good under tension. So banana is a very good example for understanding the mechanical behavior of mature trees. And in addition, it cracks perpendicular like that. And the banana doesn't break that way. Yeah, that means the failure mechanism, what happens in a carrot, does not happen in a tree. Well predictable where it will break, mostly at the transition from bigger to smaller diameters, because diameter is taken to the power of 3. So any significant change in the diameter and in the shape creates so-called notch stresses. Is that the right term, I think? And this leads to the fact that there is an initial failure. But here, even here, the initial failure, always microscopically, is a crack, a horizontal failure. Yeah, that means even there it happens like this. Not like in the carrot. The carrot is, again, it's completely different. That means in an asparagus, it's a good model for a young, intact tree without defects. And then we know where it breaks. Yeah, so celery? Yeah, okay. So you can easier find out that the direction of loading is important. So you can feel what is the strongest, what is the weakest direction. So what is the strongest direction for a celery? To the side, this one, because that's the maximum diameter. Yeah. So it's so simple. And then what is the easiest way to break it? Is it against or into? Into, yeah, that's the easiest way. When I did that, I showed that on a meeting in the United States. The whole crowd was going crazy, but I was never anymore invited by that group. Obviously, some people complained about the European guy, because in the shop they were called beef frank, and these were Italian salami. And I thought, that's not fair. This is even bigger than this one, but why is this stiff up and this is so floppy?
density.
Moisture content. Yeah, this is one of the reasons why all our measurements heavily depend on moisture content, because the stiffness of wood depends on moisture content and the density. So the wind, the high wind, really changed the size of the crown. Compared to no wind, the size of the crown under full winds is about approximately, you see that? Approximately 20% smaller. Yeah, that means this one, even with maximum wind speed, the total crown size didn't change. The next one, the tiny one, the poor guy. Not much of a change of the size. And the palm did exactly what it was proposed to do, because it acts like a young tree. It gets smaller. So the size of the crown goes down by nearly 50%. The wind drags on the leaves. This one has the lowest, by far, wind drag, because the wind just goes around the surface of the crown. That means the denser the crown, the better it's closed, the lower the wind load. That owned that tree was an iconic tree. They said, we would like to have it inspected because we're not sure about the safety of the tree, and only a few limbs going out here, then it's hard, sometimes impossible to do a pulling test. When you would like to pull here on that tree, first of all, you would destroy the stem head. The company said, okay, pulling test is not possible, so we do a sonic tomography. Fortunately, they did one mistake. They did not make one mistake, a typical one. Sonic tomography, I hope I can show you that tomorrow. The sensors should not be placed too deep. So they placed the sensors correctly here, and they said the tree is fine. What I did was very simple. I took the resistograph and I drilled in, I think, 5 or 6 of the 8 or 9 buttress roots. In none of the buttress roots I had more than 10 centimeters of wood. All other wood was gone. The decay was only in the root system, down here. So the sonic tomography was done correctly, it was interpreted correctly, but the decay was one level down. And by not drilling, there was no chance of detecting it. That means these cases you can only identify the decay, you can only identify when you drill down here at the base of the stem into the buttresses. And this is one of the reasons why I always recommend to have all the technology in the back of your car, and then depending on the tree and the challenge, decide which method is the best.
Day 2, Advanced Tree Decay Detection Workshop. You can hear the buzz.
Those are the two with the most prominent features where it's visible on the outside.
Okay.
And this is a prize open.
And if you look, there's this really old picture here, probably from the maybe the 30s, 1930s, when this was the Hendry farm, the Hendry family farm.
The likelihood of having included bark between the centers is quite high, and here you see it. There's included bark. Okay, here it's only until this height. The outermost points of the stem carry most of the load. This is why there we have to place the sensors. You don't need to follow me because I will come back on the other side. Done for all the nails around the tree.
I can make that desk.
Oh yeah, this one.
Close the top. And we'll put the other one on.
As soon as there's anything frozen in the tree or even in the outer sapwood, forget it. The results are just ridiculous. It doesn't make any sense.
Oh, there is a question. Does it work on that?
It works in parallels. And the circumference is about 5 meters and 85. I'm not used that someone lies in front of me on the ground. So, and based on that picture now, the machine could calculate a tomography picture already. Like 5 or 6 times, the mean square error of the measurements from sensor 1 goes down below 5%. That's perfect. I could go this way or that way, so I could start at sensor 4 or 7 or whatever. It doesn't make a difference. Especially when there's a lot of traffic, I'm tapping 10 times. Can you tap on any of the sensors? Just one time? Okay. So that's the first measurement. And then...
Show everybody that again, Frank?
Yep. On every sensor one time, please.
Wow, that's crazy fast.
Does the firmness of the head make a difference?
Yeah, it does. A bit. Fortunately, not a strong one.
You never use a spring-loaded hammer that would be consistent all the way around?
Yeah, good idea. I will talk about that quick.
It's 2023, and we're here at the RBG with
Frank Rinn.
and these guys and gals have been learning all about
Biomechanics.
turn to someone your left to right, give them a high five and say I love biomechanics.
Biomechanics.
Right on.